Class 11th, Subject Physics, 9th chapter, Optics. From this chapter, let us see some of the formulae. The first formula gives speed of EM waves, that is speed of electromagnetic waves in a material medium. In a material medium. So when the electromagnetic waves, that is light waves, travel through any medium, at that time the speed of EM waves C is equal to 1 upon square root of epsilon mu. 1 upon square root of epsilon mu, where epsilon is the permittivity of that medium and mu is the permeability of that medium. Instead of any material medium, if there is vacuum or free space, then when these electromagnetic waves travel through vacuum or free space, at that time its speed c is equal to 1 upon square root of epsilon 0 mu 0. 1 upon square root of epsilon 0 mu 0, where epsilon 0 is the permittivity of the free space or vacuum and mu 0 is the permeability of free space or vacuum. If we put the values of epsilon 0 and mu 0 in this relation, then we will get value of the speed of electromagnetic waves, which comes out to be 3 into 10 raised to 8 meter per second. Now let us see second formula, which gives the absolute refractive index of any medium. Absolute refractive index of the medium, that is refractive index of any medium with respect to air or vacuum, and that is n is equal to c by v. N is equal to c by v. N is the refractive index of that medium. C will be the speed of light in air or vacuum divided by the speed of that light or electromagnetic wave through that medium. So velocity of light in air divided by velocity of light in that medium, which will give us the refractive index of that medium, which is the absolute refractive index of that medium. Then third formula gives the Snell's law. It is Snell's law, which gives the relation between angle of incidence and angle of refraction. Angle of incidence and angle of refraction, that is angle I and angle R. And therefore, here if N1 and N2 are the refractive indices of the first medium and second medium, then N1 sin I equal to N2 sin R. N1 sin I equal to N2 sin R. And therefore, in this case, I will represent angle of incidence, R will represent angle of refraction. From this formula, we can write N2 by N1 equal to sin I upon sin R. N2 by N1 equal to sin I upon sin R. But that N2 by N1 will be the relative refractive index of that medium, and therefore it will be represented by N, and therefore we can write N is equal to sin I upon sin R. N is equal to sin I upon sin R. Then fourth formula is for number of images formed between two plane mirrors inclined by angle theta. So if there are two plane mirrors and if they are kept inclined with each other by angle theta, then the number of images formed n is equal to 360 divided by theta. N is equal to 360 divided by theta. So this n will represent the number of images formed, and then actual number of images observed will depend upon this value of n. And therefore, in the first case, we can say that if n is even integer, then the number of images seen or observed will be n equal to n minus 1. N is equal to n minus 1. Second, if n is an odd integer, and the object is at angle bisector. So if n is odd number and the object is exactly situated at the angle bisector, then n will be equal to n minus 1 again. N is equal to n minus 1. Instead of that, third, if n is an odd integer again, if n is an odd integer and now the object is of angle bisector. If the object is of angle bisector, that is within angle bisector, then n will be equal to n. N will be equal to n. Fourth point, if n is not an integer, if n is not an integer, if it contains some fraction part, then n will be equal to m. N will be equal to m, that is integral part of n. Integral part of n, that m will represent, this m will be the integral part of n. That is the part before decimal point will represent the number of images seen. Then fifth equation gives focal length for any mirror. Focal length f will be equal to r by 2. F is equal to r by 2, where r is radius of curvature for that mirror, and the focal power p will be equal to reciprocal of focal length, that is p is equal to 1 by f. This is the focal power. Then next relation gives sixth relation between u, v and f. Relation between u, v and f for a mirror, where u is the object distance, v is image distance, f is the focal length. Now for any mirror, the relation between these three factors will be given as 1 by f is equal to 1 by v plus 1 by u. 1 by f is equal to 1 by v plus 1 by u. Then seventh formula gives the relative refractive index of any medium. Relative refractive index of any medium, that is refractive index of second medium with respect to first medium. Refractive index of second medium with respect to first medium will be equal to ratio of refractive index of second medium to the refractive index of first medium, that is n2 by n1, which will be equal to velocity of light in first medium divided by velocity of light in the second medium, that is v1 by v2. Then eighth formula is for refraction at plane surface of water. If there is refraction at the plane surface of water, at that time we can find the refractive index of water by using the formula real depth upon apparent depth. Real depth upon apparent depth, which will give us the refractive index of water. Real depth upon apparent depth. Then ninth formula gives for any thin lens. If you consider any thin lens, then for any thin lens we can write 1 by f is equal to 1 by v minus 1 by u. 1 by f is equal to 1 by v minus 1 by u. It is for only thin lens. Then 10th formula gives for refraction at a single spherical surface. If the refraction takes place at a single spherical surface, then we can write n2 minus n1 upon r. Refractive index of second medium minus refractive index of first medium divided by radius of curvature of that spherical surface. So n2 minus n1 upon r will be equal to n2 upon v minus n1 upon u. n2 upon v minus n1 upon u. Then 11th formula gives lens maker's equation. Lens maker's equation, which is stated as 1 by f is equal to n minus 1 into 1 upon r1 minus 1 upon r2. 1 by f is equal to n minus 1 into 1 upon r1 minus 1 upon r2, where n will be the refractive index of that material of the lens, and r1 will be the radius of curvature of first surface, r2 will be the radius of curvature of the second surface, and therefore 1 by f is equal to n minus 1 into 1 upon r1 minus 1 upon r2 gives lens maker's equation. Then 12th formula is for a prism. So in case of a prism, a plus delta is equal to I plus E. A plus delta is equal to I plus E, where A is angle of prism, delta is angle of deviation, I is angle of incidence, and E is angle of emergence. So for a prism, A plus delta is equal to I plus E. And now let us see next one, that is 13th formula gives the prism formula. In case of a prism, the refractive index of material of that prism n will be given by prism formula, that is n equal to sine A plus delta m by 2 divided by sine of A by 2. N is equal to sine A plus delta m by 2 upon sine of A by 2, where A is angle of prism, delta m is the angle of minimum deviation. Then 14th formula is for a thin prism. For a thin prism, that means if that prism is having very small angle of prism, then we can say that it is a thin prism. So that for that prism A will be small. The angle of deviation for such prism, angle of deviation delta will be given as A into n minus 1. Delta is equal to A into n minus 1 for thin prism. Then 15th formula gives the angular dispersion. Angular dispersion, which is given by the formula angular dispersion delta V minus delta R, delta V minus delta R, which is equal to A into NV minus NR. A into NV minus NR. NV is the refractive index for violet color and NR is the refractive index for red color, and hence mean deviation will be given as, mean color is considered as yellow color, and therefore mean deviation delta y is equal to A into ny minus 1. Delta y is equal to A into ny minus 1. Then 16th formula gives the dispersive power. Dispersive power omega is equal to Nv minus Nr upon Ny minus 1. Nv minus Nr upon Ny minus 1. 17th formula gives for two thin lenses. If you consider two thin lenses, then for two thin lenses in contact, if two thin lenses are kept in contact, then we can write 1 by f is equal to 1 by f1 plus 1 by f2, where f will be the focal length of combination of the two lenses, that is effective focal length, will be equal to, that is 1 by f is equal to 1 by f1 plus 1 by f2. Then 18th formula gives the magnifying power of simple microscope. The magnifying power of simple microscope, that is a reading glass, that m is equal to d by u. The magnifying power of the simple microscope or reading glass is m is equal to d by u, where d is the distance of distinct vision and u will be the object distance. Similarly, 19th formula gives the magnifying power of compound microscope. Magnifying power of the compound microscope. In case of compound microscope, we can define two magnification, that is linear and angular. So linear magnification will be equal to MO equal to phi-O upon UO. MO is equal to phi-O upon UO. That is linear magnification will be equal to, it is the ratio of phi-O and UO. Phi-O will be the image distance for objective and UO will be the object distance for the objective. Similarly, the angular magnification will be given as ME equal to D upon UE. D upon UE, where D is distance of distinct vision and UE is the object distance for the eyepiece. Object distance for the eyepiece. Then 20th formula gives the magnifying power of a telescope. Magnifying power of a telescope, which will be given as m is equal to FO upon FE. FO upon FE, where FO is the focal length of objective, FE is the focal length of eyepiece. and the length of the telescope will be equal to length of the telescope L is equal to FO plus FE, focal length of objective plus focal length of eyepiece. And so these are some of the formulae in case of optics.